Part D of Module 1, Optimality of Algorithms, and Project 1. Our main topic of this part, Optimality of Algorithms. This is the last part of Module 1. Starting from tomorrow, I will start Module 2. So you can see we are moving pretty fast. All right, D.1, minimum selection problem. So let's look at the problem we want to study in this video. First, let me give you the question. So you can see this is our problem number 3 in this class. Find the minimum of an array. That's pretty easy, right? I believe everyone in this class can find the minimum of array easily. But here, I just want to use this simple example to introduce a very important concept, optimality concept in algorithms. Let's look at the question. Given an array in this expression, you know the meaning, find the index I such that A of I is the minimum of the array. Pretty simple, right? Yeah. So first, let me, quickly go through the algorithm. Then we have our discussion on optimality issue. All right. The problem type. Remember, for this class, we will learn 3 basic problem types. So let me list. Search 1, selection 2nd, and sort 3rd. 3 basic problem types for algorithm class. Here, this is a selection type. So what's the selection problem? Let me give you the general definition of the selection problem. Find the kth smallest element, kth, given that integer k number. Okay? So the k in this reasonable range between 0 and n minus 1. Right? Now, we need to find the kth smallest element in the given array. That is the general selection problem. Our minimum problem, that is a special case. Oh, yeah, here. All right, kth smallest. All right, let me modify a little bit. Because when we talk about kth smallest, we better put the range between 1 and n. Right? Because we can say first smallest. We cannot say 0th smallest, right? So the counting is starting from 1, not 0. All right, so let me modify it. All right? So for that reason, k equals 1, that is the smallest, the minimum. First smallest, no, the minimum. All right, so that's the range of k. But for the general case, solving this problem, that's not easy. That is very complicated. In our Module 4, we will learn that. In our Module 4, when we learn divide and conquer approach, we will solve this problem completely. Very, very complicated. All right, so let's here, let me just give you the reference in the textbook so you can study these 2 sections, try to get a little more understanding. All right, so here, let me start my analysis. All right, so think about our typical implementation steps. At the beginning, we do initialization. So we create a main variable. We want to store the minimum value in this variable, but we maintain the value of this variable dynamically. right? Or we can say we put the currently minimum value in our processed elements. Currently minimum value in our processed elements, because when we process the whole array, we process one by one, right? Until we finish the processing of the whole array, right? But at certain point, we only process part of the elements in the array. Yeah. So we store the minimum value in the processed part. Yeah. But after we finish processing the whole array, we get absolute minimum of the whole array. That simple idea. All right. So at the beginning, the minimum value equals the first element, a of 0. Okay? That's the initialization step. Then the general step. So at each step, we need to do one comparison. Compare min value with the value of the current element, a of I. Okay. So when we do that comparison, we have two possibilities. The first one, min greater than a of I. In that situation, we get a smaller value for some element in the array. We should update the value of the min variable. So we do this assignment. Okay, we find a smaller one, so we should update it. Yeah. So we should make sure it is always stores the minimum value of the currently processed array elements, more precisely. Yeah. Otherwise, no replacement, just move to the next element. We do iterations. In the next iteration, we compare min with a of I plus 1 until we reach the last element where I equals n minus 1. We finish comparing with all the elements in the array. So we can produce the output. What is the output? Right? What is the output? Finally, return the min value. Return the min value, probably including I, location in the array. Yeah. Because that location in some of the applications could be useful. So we may like to include it, if necessary. Yeah. All right. Yeah. Now, the next thing, during this procedure, okay, all right, let me ask you how many comparisons we have done to get the answer. Can you count it? Another counting question. Counting. Yeah. We need to do another counting. Yeah. But this time, we cannot use counting by reference, right? Yeah. That method may not work all the time. Sometimes it doesn't work. So here, it looks like this technique does not work. All right? Then we need to use another view. Yeah, so let me look at the view. All right. Yeah. Think about the procedure. So let's start from the very beginning. When we do initialization, there is no comparison, right? So this is assignment. Okay, just the assignment operation. Although it is an operation, but we do not count it. We only count the number of comparisons. Okay, yeah. So we don't count it. We only count number of comparisons. All right. So for the first element, we do not make any comparison. But other than the first element, for all the remaining elements, one comparison for one element for one comparison. Okay, yeah. So one element for one comparison. For all elements except the first one. Okay, yeah. One element for one comparison except the first one. How many comparisons? How many elements do we have excluding the first one? That's simple, right? That's simple. Okay, n minus 1. Total n elements, but we exclude the first one. So we have n minus 1 elements to be used to compare with mean value. So we get counting number. Yeah. But here you see this one-to-one. It's like one-to-one correspondence we used in counting by reference. Yeah. If you want to treat that way, it is okay. If you treat in that way, we apply the counting by reference. It is fine. Yeah. But that's not important. The most important thing is we get the answer, n minus 1. Okay? All right. The question, are you satisfied with this answer? Right? Is it a good solution? Yes, we need to answer that question. But that question may not be easy to answer. Okay? All right. So now let's look at that pretty hard question. Is it possible to further improve the algorithm? We always need to ask this question after we get a solution. So here, it is time to answer this question. There are two options for this question. The first one, we can improve. Yeah, it's possible. So we should improve the algorithm. First option we can take. But there is second option. You cannot improve. It is impossible to improve it because it is already the best algorithm, right? Already the best. Yeah. But in that situation, you need to do one thing. You need to convince people that this algorithm is really the optimal one. Nobody can improve it. This step is pretty hard. So for this example, this is our goal. We need to show our algorithm is optimal. So this is the key part in this example. Yeah. All right, so let's look at that. But why it is so hard here. Yeah. The hard part, so let me point out why it is so hard. Yeah. The hard part is we need to do this kind of thing among all the possible algorithms. How to show that this one is optimal among all the possible algorithms. Because solving this problem, people can use all different kinds of algorithms, all possible algorithms. Okay? But the hard part is how do we understand these all possible algorithms? From the language point of view, we know its meaning, but do you understand some hidden implication behind it? Like they should include unknown algorithms, right? All the possible algorithms should include unknown algorithms. Unknown. Can you study unknown algorithms? Nobody knows the detail of that algorithm. How can we study unknown algorithms? Think about that. Later you will see it is possible. Even there are, countless unknown algorithms, but we can still study those unknown algorithms. It's possible. At the end of this video, you'll see example. All right, so let's do that hard part. All right, unknown part. All right. The question, how do we convince people that our algorithm is optimal? Yeah. All right. For this one, we need to really use some critical imagination based on our real-world experience. Remember, in problem solving, understanding of the problem or our view of the problem, view angle, we can take different views, different view angles of the problem. Very important. Here, we need to choose a good view for this particular problem. Yeah. So what's that? Real-world experience. What do you mean real-world experience? We need to borrow some real-world experience. So when we use that view, that angle, we can see the insight quickly. So that's the reason. Insight. We need to find the insight. If you do not take the right view, it is very hard to find the insight. So we need to get that critical view. All right. Here I use this connection. So what kind of connection? Comparison. Comparison operation. We want to study comparison operation in this particular problem. But in the real world experience, I use sports match, a match in sports games. Okay, so we're familiar with that, right? A match competition between two players. All right, yeah, we use that kind of connection. Yeah, all right. Then when we establish connection, let's make this kind of reasonable assumptions, connections. Yeah. So what's that? Less than, yeah, in comparison, we get less than case, right? Less than case. One element is less than another element. Less than case corresponds to win in a sport match. Win. Why win, not lose, right? Less than, based on your intuition, it should be lose case, right? Yeah. Remember, the goal of this question, find the minimum. The smaller, the better for us, right? Because our interest is at the minimum, not the maximum. If we need to find the maximum, you can define greater than as the win. But now our interest is at the minimum, then we need to take the opposite assumption. So less than would give us a win result in a sport match. Yeah. All right, so that's easy. So we need to switch, understanding a little bit. Equal, just tie. Greater than, lose. Lose. Okay? Yeah. 3, status. Yeah, we need to consider. Yeah. Now, with this kind of connection, we can understand our solution. Optimality of our solution. Yeah. So let me give you the convincing arguments. Yeah. Think about if my arguments can get you convinced, this solution is the optimal. All right, I have a list of arguments. Okay, try to follow my, interpretation. Yeah. All right. The first one. Imagine that Ming is the final winner. Yeah. The minimum. This player beats all the other players. So it is the final winner. Okay. Beats in terms of comparison. Comparison. So equivalent. Yeah. But we use a different view so we can see the inside better. Yeah. Here, let me show you how to get that insight. Yeah. it needs to beat all the other elements in the array through comparisons, through matches, comparisons, equivalent. All right. Directly or indirectly. See? Directly or indirectly. See? This is important. Directly. Yeah, we know that. A less than B. Yeah. A less than B. So there is one match between them. So A beats B. That's easy, right? Yeah, this is a direct case. But indirect case, if we know B less than C, that means B beats C. Okay? Do we need to do a competition between A and C? We don't. Because by the transitive property, remember this comparison, we have the transitive property. Based on the transitive property, we can make a conclusion A less than C. If A already, so by A less than B, B less than C, we already know A less than C. Why we need to waste another match between A and C? We don't need to waste a match between A and C. So we skip this match. Skip this match. Okay? So we call it indirectly. A indirectly beats C. That's the meaning. Okay? All right, so we take that. That is allowed in our tournament arrangement. Tournament. Okay? Yeah, here. So let's continue our arguments. So the next one, yeah. If an element loses once, it is eliminated because that element has no chance to be the winner, final winner. If one element loses, that means some other element is smaller than that, so this one cannot be the minimum. So why we need to consider it again? We should not consider that loser another time, right? Yeah. So it is eliminated. So here, this word is important. Eliminated. Eliminated. Yeah. Eliminated because this corresponds to the method we use here. We call the elimination method. Yeah, so let me use this. Elimination method. Okay. Remember, we are looking for insight, right? What's the insight? The elimination property is the insight of this method. All right, so let me keep going. Yeah. Each comparison can only eliminate one element. Is it possible one comparison, one match eliminates two players? No, right? One winner, one loser. How can you eliminate winner, right? It's ridiculous. You can eliminate the winner, right? Zero elimination, no loser. That's not right, right? Tie. Oh, you may argue tie, okay? Because in the tie case, the value of the main variable will not be replaced, okay? Because the current minimum has not lost, right? The current main element has not lost. Why will we replace it, right? So even a tie, we don't replace the current winner. That's just like, world champion, one player challenge the current champion, right? But if you cannot be the current champion, you just get tied. You cannot defeat it, right? You cannot replace the current champion because you have not won, something like that. You have to completely beat the current champion. Yeah. All right, so let's continue. Yeah. We need to eliminate n-1 elements. Thus, we need at least n-1 comparisons. To eliminate one element, we need one comparison, one match. Okay, one-to-one correspondence, right? One-to-one correspondence. So here you can see we use that counting by reference idea another time. One-to-one correspondence. One eliminated element corresponds to one comparison or one match. We know to get a final winner, we need to eliminate n-1 elements. That means we need at least, here you can see, we need at least n-1 comparisons. Okay? But our current algorithm, we have that. Our current algorithm, we have that exact n-1 comparisons. That means our current one is the best. Okay? So our current one is the best. Yeah. All right, so at the end, the conclusion here, I want to summarize. We use the elimination method here. Elimination method here. Yeah. Try to eliminate as many as possible elements. That's the elimination method. Now, later you will see we will use elimination method many times. All right, so let me stop our first video of part D right here.